Hello, welcome back. So during our last theory discussion, we presented the general expression for the total potential energy, and then we derived the stiffness matrix for the strain energy term. So we have all these different terms. We have the integral over the length, and now this is in 1D, so we just have dx. And we had this term that we derived. We also have the body forces, the tractions, and the point loads. We took this continuum body with these integrals and we split them up. We said, all right, the continuum has now been discretized into fine elements, and then we can write the strain energy for each element. So we've moved that integral over the element, and then we're going to sum up over all the elements. So that's a major step that we took from here to here by using that mesh discretization. We simplified that equation once more by summing, calculating, moving this integral into something called U of E, and then this strain energy is summed up over all the elements. U of E is just that integral over the element, and this is called the element strain energy. And we use that to develop the elemental stiffness matrix, a major step in our learning this semester. Here's just a little snapshot of it, just real quickly. We had our mapping that we used, our isoperimetric mapping, and we had the derivative of psi with respect to x, which is given here. We could rewrite that to write x, and of course this dx is used in the integral, the elemental integral that we just showed here. Okay, so we're using it to switch parameters. 2x2 minus x1 is just LE, so then we can move this in the integral. So then our elemental integral, we had our elemental displacements, our B matrix, derivatives of shape functions, our material properties, and then we could substitute this dx. We could put in d psi in there. So that allowed us to write an equation like this, and then we integrated B transpose B. We computed that, which gave us 1 over LE squared, and then with a square matrix with 1s and -1s in it. We did the integral over d psi from -1 to 1. That's our master element. So by introducing this transformation, we were able to put it into master space, master element space, if you will. All right, and then we were left with the total elemental strain energy is 1/2 Q transpose times the quantity AE E sub E LE. Okay, so these are all properties of the element. Then we had some 1s and -1s. So that leaves our elemental stiffness matrix. We're going to call that K sub E, looking something like this. All right, so we made that elemental move. What we need to do now is continue our discussion on the force vector. So every term in that equation, every term here, we actually need to derive. Okay, so now we're moving on to this one. This one's actually pretty easy. There's no integral sign, so we don't have to do it. We're going to have to do force and tractions. So we're going to do that real quick now. So let's start by writing that term here. So we have U transpose F. So remember that these are the displacements, okay, and we have cross-sectional area. And then we have this term here, which is the body force per unit length or volume. In this case, it's just length. Okay, so we can write, remember U was equal to N1 Q1 plus N2 Q2, and that was equal to N underscore Q. Note that these are a 1/2, a 2/1, which leaves us with a scalar 1/1, which is U. And remember, when I draw the line underneath these, that means it's a vector. F and E, F and A sub E are constant. Throughout the element. And so we can move this out of the integral. Okay, so then we can write our terms a sub e and f outside of that integral, the integral over the element, and then u transpose. U is a scalar, so the transpose really doesn't mean much. N1 plus Q1 plus N2 Q2, and that's over dx. So this is good, but we'd like to write this in a matrix form so we can implement it more easily into the fine element program. So is there a way that we could actually write this in matrix form? Let me put an equal sign here. So we could actually write this is equal to Q transpose, the bar there. And we're going to have a sub e f times the integral over the element n1 dx and a sub e f, the integral over the element n2 dx. Okay. So that we can multiply through, so it'd be q1 a sub e f integral over e n1 dx plus q2 a sub e f, the integral over the element n2 dx, which we can further rearrange, and that's equal to a e f integral over e, the quantity n1 q1 dx plus n2 q2 dx. So what did I do? I basically just showed that these are the same. These are the same. So I just showed that writing a form, using a form like this is okay. Okay, so, all right, then we can evaluate these integrals. Element, so we have the integral over n1 dx. That's going to be equal to 1 minus psi over 2. Okay, and we have dx. That's equal to -1 to 1, 1 minus psi over 2, le over 2. Then d psi, our substitution. So then we're going to have le over 4, pull that out, and then it's going to be -1 to 1, 1 minus psi d psi. If you go ahead and compute this integral, then you're going to be left with le over 2. Okay, so the important point is this step here. When I made the substitution, remember that came from d psi dx, which we know psi, right? It's a function of x. It's 2 over x2 minus x1 equals 2 over le, which implies that dx is equal to le over 2 d psi. So that allowed me to make that substitution. Okay, it turns out that for the integral n2 dx that we also have, that gives us the same thing, le over 2. There should be an e over there. So now we can plug these values back into our equation. Say substituting back in. We have our expression, which would be the integral over e u transpose f a dx is what we started with. That's going to be equal to qt and then AEF-LE over 2, that integral we just computed, AEF-LE over 2. Make this a little longer here. And we can also write that, if we'd like, as a matrix form, which is just QT transpose FE. Okay, we call the vector FE, A sub E, L sub E times F over 2 times 1, 1. We refer to this as the elemental force vector. Okay, so for every truss element that we have, again, we're looking at something like this, 1 and 2, that we assume that F is constant throughout this element, and we would compute these for every little segment that we have this elemental force vector. All right, so that wraps up the force calculation. Next, we can derive the traction vector, which is the last term we need besides the point loads in the total potential energy equation.